Hi, welcome to lecture 3.1 of the SAGE-based course on Monte Carlo methods. I'm Raz, I'm your instructor for this course. So let's get started. Stat 221 at the University of Canterbury. So we are going to be in week 3. Week 3 is on the topic of conditional probability, random variables, expectations, loops, and conditionals. So let's go to the published worksheets. I logged in as Kriti Yogi already, and please log in as yourselves with your usernames, and let's grab Stat 221 Week 3 from the published worksheets. Make sure that I was the one who published it. Now once this has loaded, we start by editing a copy. So there you are. Stat 221 Week 3. Conditional probability, random variables, loops, and conditionals. So let us recap last week's material on probability. Recall that an experiment is an activity or procedure that produces distinct or well-defined outcomes. The set of such outcomes is called the sample space of the experiment, and the sample space is usually denoted by this Greek uppercase symbol called big omega. An event is nothing but a subset of the sample space, and probability is just a function that assigns numbers in the unit interval of real numbers between 0 and 1 to events. So in other words, probability is just a function that goes from the set of events to the unit interval. But it's not any old function. Remember, this function called probability satisfies the following axioms. Okay, so for any event A, this function, the probability of A, must be between 0 and 1. Well, that's fine because the range is between 0 and 1. If capital omega is the sample space, then probability of the sample space is 1. This is again another property that this function P should satisfy. If A and B are disjoint, that is, A intersection B is the empty set, then we want the probability of A union B to be the probability of A plus the probability of B. Remember, A union B, A and B are events, so they are in the domain of this function called probability, or P. And whenever you have two disjoint sets, then the probability of the union should be their sum. That's the third axiom that should be satisfied by P. Now this one's a bit more tricky, I pointed out, and somewhat controversial, but we'll just assume it as a given axiom that's satisfied by all the probabilities we'll see in this course. So if you have an infinite sequence, a countably infinite sequence of events A1, A2, A3, ... such that they're pairwise disjoint. That means if I take any two distinct events AI and AJ, they can't be the same. I is not J. So if I take any two distinct events AI and AJ from this infinite sequence, say A1 and A13 or A43 and A94, such that their intersection is the empty set, then the probability of that infinite sequence of pairwise disjoint events, which is on the left side here, is simply the sum of the probabilities of the individual events. Okay, so that's nothing but an extended axiom 3. Axiom 3 applied to an infinite sequence. Now, when these four axioms are satisfied, we say we have a probability from the set of events to the unit interval 0, 1, and sometimes we refer to these set of events or the domain of the probability as a sigma field or a sigma algebra. Property 1, okay, so these properties just pop out of this axiomatic definition of probability. Remember from last week. Property 1 says probability of A is 1 minus probability of A complement. Okay, where A complement is the set difference of the universal set or the sample space capital omega, take away A. Okay. Property 2, for any two events A, B, probability of A union B is probability of A plus probability of B minus probability of A intersection B. Again, this is another property that just pops out of this definition of probability. Okay, the idea in property 2 generalizes to what's called the inclusion-exclusion formula. Okay, so this is slightly new material now, going beyond review. Let A1, A2, dot, 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 AN be any n events, then the probability of the union A1 through AN is equal to the sum of the probabilities of AI as I goes from 1 through n minus the pairwise intersection probabilities plus the three-wise intersection probabilities and so on and so forth. So you have a negative 1 to the power of n plus 1, which is an alternating sign. So essentially, in words, we take all possible intersections of 1, 2, 3, and n events and let the signs alternate to keep correcting the double counting and the uncorrecting the triple counting and so on. Okay, so once again, this is just an extension of the property 2 to more than two events. Okay, here's a question. Does the inclusion-exclusion formula agree with the extended axiom 3? That is, if A1, A2 up through AN are pairwise disjoint events, then the probability as I goes from 1 through n AI is equal to the sum as I goes from 1 through n of probability of AI. Well, this is a good time to pause the video and take a quick look at what the question is asking. It's asking if this formula upstairs, the inclusion-exclusion formula, simplified to this formula. See, the left-hand sides are the same for these two formulas. Does this formula simplify to this formula if we actually have pairwise disjoint events for A1, A2 up through AN? Well, pause the video and make sure you can understand and answer this question. Alright, go ahead and pause the video if you haven't already and try and answer this question. Okay, the answer to this question is clearly yes, because we are given events that are pairwise disjoint. So because they're pairwise disjoint events, the probability of their intersection is 0 because it's the probability of the empty set due to their pairwise disjointness. Because they're pairwise disjoint, this again is an empty set, and this again is going to be an empty set. So all of the values for the probabilities besides the first term here will be zeros. Okay, so yes, indeed, this formula does hold from here if we have pairwise disjoint events. Now let's move on to the next topic, the domain of the probability function. So here we want to understand what exactly is stipulated by the axioms of probability, about the domain of the probability function, right? We said all these things the probability function should satisfy, so that clearly has implications for the domain, right? The function always comes with a domain. So these are going to be formalized now. So the domain should be a so-called sigma field or sigma algebra, and it's denoted this short form, sigma field or sigma algebra, and it's denoted by sigma of capital omega, sigma of the sample space, or just script f for the field. Okay, so it's a calligraphic script f. It's not a usual capital F or a usual little f, such that the sample space belongs to the sigma field. If an event A is in the sigma field, then its complement is also in this collection of events or the sigma field. And if A1, A2, dot, 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 a countable collection of events are in the sigma field, then so is their countable union. So thus we say that the domain of the probability is not just any old set of events, but rather a set of events that form a sigma field that contains the sample space, is closed under complementation, and is closed under a countable union. We say it's closed under because complementation, because if A is an element of F, then A complement is also an element of F. So we say the collection F is closed under complementation. Similarly, if we have a set of events and all of them are in F, and that implies that their union is also in F, then we say F is closed under countable unions. Now we finally have the probability space, or the probability triple. It involves these three objects. So we have an ordered triple. The first one is the sample space, capital Omega. The second one is the sigma field over that sample space, or script F of omega. And the third one is the probability function that has F of omega, or the sigma field, as its domain, and assigns numbers in the unit interval 0, 1 that clearly satisfies these three axioms, and the fourth one as well. So just put them all in perspective now. It's a good time to pause the video, go back, recollect, see all these things in your head once more. Let's move on to examples if you're ready. So in example 1, let the sample space be head and tail. What sigma field could we have here? So this is the coin tossing experiment. Well, one sigma field is that we have head and tail. The entire sample space should be clearly there. The empty set should be there because it's closed under complements, remember? So this is the full space and its complement is the empty set. And of course the complement of the empty set is the full space. And we could have H, and H's complement is T. So this satisfies complementation, and when you take unions of any of them, you'll get the output, the union set also in there. So this is the finest sigma field, because you can't get any finer than that for a two-element sample space. Now here is F prime of omega. Here is another sigma field. This is called the so-called trivial sigma field. Here all you have is the sample space, right? Yes, that's fine. Its complement is there, and that's it. So in this sigma field, you have only two events. Either the coin lands heads or tails, or nothing happens. Okay, so as opposed to this collection of events where the coin could land either head or tail, that's an interesting event. The coin lands heads, that's an event. The coin lands tails, that's an event, or well, nothing happens. Okay. Now here's another example. Let capital omega be little omega 1 up through little omega n. So you have n distinct outcomes. So generalizing the previous argument to any sample space with finitely many n outcomes, we have the sigma field. The finest sigma field is the power set of omega. So this is, remember, 2 to the omega from last week's material. It's the set of all subsets of omega. It's also known as the power set. And the size of this is 2 to the n. So there you go. There is always a finest sigma field you can define on a finite collection of outcomes.